Yeah, this is going to be a quick walkthrough. There's a library function that's called control analog absolute. It's a PID controller, and we're just going to walk through it pretty quick. It's documented, it's overly documented, it's written a statement on every line. So you're just going to talk through what's the purpose of this. So here it is, the input-output interface. What's in here in the variables, it's the code we are going to look at. It's not, yeah, it's the code. I can get rid of this one too. Yeah, maybe we could do a little zooming in here. So you could look at your comments over here. They're just going to disappear. We can get rid of this one too. Okay, now I'm probably sitting a little over the comments. That's all. You should document it like this. This is 4 years old and written by me. So it tells you about what your control algorithm does. But in general here, get a first scan, or we need timing, sampling time, and so on. So here, populate our temporaries, assigned values to our temporaries. And then here, validate all the inputs. Let's say the automatic mode set point must be between 0 and 100. The manual mode set point and this feed-forward values has to be between 0 and 100. And the input should be in the range for this automatic, or the maximum value, a minimum value for Simatic S7. And other PLCs, of course, these will be other values. So what we do is that we just scale. We say this is a unipolar input, so we scale this or process value to percent. Calculate the error, because the PID controller is working on an error. Handle the restart, initial our timing system. The integral that we had 2 days ago, or whenever we have had it, is 0. And the control value is output is set to 0. And my old error that I'm going to use in my differentiation and so on is set to the error I have now, so I don't get a jump, just have to restart, and so on. Here is the sampling timer. So calculate automatic. If I'm in automatic times, each time my sampling time expires, I do a calculation. And for fast CPU, make sure that the sampling time, the calculated sampling time, is greater than 0 seconds, as you're going to divide by 0 here, and that's not too good. The bumpless here is that when we are changing mode or parameters and something like that, there shouldn't be a bump on the output. So that's what bumpless is. And here we just calculate the times to, let's say, engineering units, because these are in milliseconds, and then we are constants, that's milliseconds per second. Just divide through. This can't be 0 because it's a constant. Actually, it's 1,000 in real. So then we have got these times in seconds, integral part. Then we have something called anti-wind up, which is if, let's say here is, when I'm going to prevent it, but anti-wind up is, if my controller is saturated, I have 100% output, there's no more juice in the system, so they can't get any more out of the system. The integration action should stop. So we just don't integrate up. I don't get any more, and when I have to switch around and integrate down, my integral value here is in 2000% or something like that, and it's going to take some time for it to get down to whatever value it should be before the output is affected. And this is true also for 0, integral wind up. So what we have, we just have a temperature. When should we integrate? When it is allowed, and if we should integrate. This is just straight for the Euler integration, first order method of integration. There's more to it. We could do it a little more fancy than that if we wanted to. But okay, if we don't have any integral action here, this internal integral values, then kind of integrating all the time is 0. Then I calculate the P, which is the error times the gain, not much to it. The derivative part, if my differentiation time, derivative time is greater than 0, I calculate. If not, my derivative part is 0. And the bumpless here, if it's bumpless, what I have a bumpless change or something. I do change something, just don't compute this differential. So we do that just by setting the old value equal to the current value. And of course, it's going to be 0, and whatever I do here is going to give me 0. And here it has to do with the sampling time here, this TT, where I checked here, it was 0, because that's this PTS is calculated based on this one. And if this one is 0, I'm kind of bad off down here in my algorithm somewhere. Here I had division by 0. That's not good. But I have checked for that further. But here you could check and say, okay, I have to be absolutely sure. I check, is this one greater than 0? Okay, and then as controller output, my output is my feed-forward value of my bias, the PID values. If it's bumpless, the bumpless only possible with a I part enable. So what we do is we say we just adjust our internal integral value to compensate for what has been calculated now in the bump by some reason or another. So I just remove that. So it's just the output he had before, what he had now, divided through by PKP. And here too, there might be possible, if I have 0 gain here, I would have a division by 0 down here. So it should probably be checked down here. Or the PKP input that we have is the PKP, yes. So here is possible with division by 0. Should probably be checked. You can fix that if you want to. And then we limit the control output to between 0 and 100%, and then we update historical values. The error I have to remember, the old value I have to remember, the old values from these set points and so on for the bumpless, and the automatic I have to remember. And bumpless transfer in manual mode. So if I want a bumpless transfer to manual, so I can enable that, and then let's just let my manual mode set point track here. And I have to write them back down here too. And in manual mode, okay, I just basically say what set point from somewhere, my manual mode set points, I just transfer it to the output. And my arrow just to prepare. So this arrow I had the last time, the static arrow that I have saved is arrow now. And as the time is t2 now. And here for the arrow, we could have used an arrow with a k index and a k-1 index to indicate that this one is the arrow that I had the last time. And I could use so also for these values here too. So it could be refined a little. And what I do here is scale the output to this engineering, the Siemens analog value range and so on. And I update the outputs here. You can, if we look back up here a little, yeah, what you could use these outputs is what you can put in the HMI system because it's in percent. So this is for your HMI if you want to make an HMI for it. And these, of course, are set points from your HMI and so on. So far, you should have detected yourself. There is one, seems like, if someone is giving me a gain here of 0 in the algorithm, I would divide through here. If I have a bumpless, here would be a division by 0, which is not nice, and you should fix it. There is an error, a small error in this program. Intentional? Maybe. Yeah. So this was a walkthrough through the control analog absolute algorithm that is in this template project. And just a quick, it's documented fairly in detail, I would say, and there is probably an error in the algorithm here. Probably. So if you test that, just test that. Have a gain of 0 and see what happens. Check what happens. So quick walkthrough.